brain-inspired perception and computation can enable scalable, efficient, real-time, autonomous robots and embedded systems. Let me introduce the organizing team. So we have Alessandro De Novo, professor in machine intelligence in Sheffield University. We have Alejandro. Then we have Iman, Ong, Davian, and Raymond. They all are here. So thank you so much for putting all the work together. In this workshop, we are already late, but we have 3 keynote speakers. We have 8 flash presentations. So flash is like really flash. So 3 minutes presentation, 2-minute question. Then we have project demonstration that we'll do, like, it's a fun interactive project that we'll show you during the coffee break. Then we have a panel discussion at the end. So we have an amazing list of keynote panels and panelists. So we have Alessandro who will moderate the panel discussion. Angelo Gangulosi is joining us as well. Andrea Czech is also here. Then Michael Mengen from Optron is already here. Daniel and Luca are keynote as well. So before further ado, I would like to invite our first keynote. So Luca is a lecturer in computer science in University of Sheffield. His research focus is on optimizing physical neural networks, adaptive computing system, configurable hardware, and efficient neural network deployment, particularly in resource-constrained environments.
Yeah, sorry for the great start. So it's my pleasure to be here today and to give start of the dances course. And today I'm going to talk about optimizing physical neural networks. So what physical neural network is? Well, it's a network where part of the computation is on the analog domain. And so rather than simulating the system through a computer, what we would like to do is to exploit the physical properties of a material directly for computational purposes. And this can be optics, membristors, spiking neural networks. There are different mediums that can be used. But today I'll try to remain general and instead talk about the learning principles and how we can optimize these types of systems. So here I'm simply denoting with that symbol the device, and that's, of course, it will operate as a transformation of some input X dependent on some parameters. Okay, so the objective is something like this. We have an ensemble of devices, an ensemble of systems, and we would like to optimize, given a task, the connectivity of the system. However, the challenge here is that the main algorithm that we use for deep neural network is backpropagation. And backpropagation assumes that feedback and forward weights are one the transpose of the other. This follows the weight transpose, the weight transport problem. Also, it assumes perfect mathematical knowledge of all the transformation in the network. And at the same time, it does not local control information. So what I mean by that is that if this is your neural network, these are the layers. Of course, the forward pass is computes the response of your system that if you want to train, your training algorithm needs to have the weights of the forward pass transposed. And also, the weight change at the layer L depends on information that is after that layer, right? So it's not local in that sense. And local would mean that your rate of change of a connection will be simply dependent on the information available there. Okay, so between those two dots. So this is quite challenging once you have a system, okay, that is physically implemented. And so backpropagation is not like, and it's really hard to deploy on chip. And there has been a lot of works trying to relax these constraints. These have been implemented in different physical neural networks, different instantiations. So these are all the different works across different years that try to relax this constraint and then implement learning algorithms on different types of devices. So here I want to give you 2 examples before going actually to what we've done in neuromorphic computing. And the first example, I think you have probably seen this many, many times, but I will provide two examples only to show you how we can approximate backpropagation, or how it's possible to still have a learning system. And one of them is direct feedback alignment. So the idea is that rather than backpropagating signal from the loss function over there, is the L, right? What we can do is that we can randomly project the gradient of that loss function with respect to the output layer through the previous layer and treat it as the gradient with respect to the activity. So it will be in backpropagation, this equivalent of setting that equivalence over there. And practically that means that rather than backpropagating through the old network structure, what we're doing is that we're randomly projecting some signal into the layer's activity. Probably you have seen this many, many times. And of course, once you do this, weight update can be performed in parallel, right? You can train all the connectivity of the network at the same time rather than backpropagation where you need to imagine this precise flow of information backwards. Okay, so only to give you an idea of some results. So how does it work in practice? Well, there was this paper in 2020, particularly showing that direct feedback alignment scales to modern deep learning standards. Now, what that means is that you can train 10-layer networks with direct feedback alignment and still find decent results. And this is the results that they managed to reproduce. This is a network trained to give you different view of an image, okay? And on the left, you can see direct feedback alignment. On the right, you can see backpropagation. Now, this is like, if you look at it, of course, you can see that it loses some high-frequency detail of the image, but still, it can provide a decent result in the context also to really deep neural networks. And of course, since it's, as you can imagine, it's not too hard to be implemented on physical neural networks because you don't need so much knowledge. Like there are a lot of constraints that have been relaxed because you don't need to have this transpose forward connectivity with the backward one. You don't have the weight transport problem. So that's been used to train physical neural networks. Okay. And here are some examples from this public recent publication where they used it for that. Okay. So another approach is that is something more recent, is the forward algorithm. The idea is that we have, in this case, layer-wise cost function. This was proposed by Hilton, 2022. And the idea is to practically have a sort of contrasted learning approach. So you have some real image, okay, and then you corrupt this image to create a negative pair, and then you define a layer-wise cost function. What you want to do simply is to maximize the activities of a layer, okay, for a real image, and minimize the activity of that layer for a fake image. So how can this work in practice is that, of course, you rely on the quality of your corruption. If your data set and your corruption are rich enough, right, then you are practically training the network to discriminate between these two pairs and to create an internal representation that is useful for also other tasks. And this also resembles a lot self-supervised learning algorithms and so on. Of course, as you can see there, like there are some tricks because it's not as easy as saying I maximize the activities and I minimize the activities. You need to have tricks like layer normalization inside and other things. Otherwise, the system is not really stable and so on. But it was shown that actually even this approach where you have layer-wise cost function can work in practice. Of course, you have some problems still layer-wise cost function, but the connectivity are one the transpose of the other. And it depends all on how you augment the data, the quality of your neural network. And this is true also for any contrasted learning, self-supervised learning algorithms, if you are familiar with those. And indeed, it can be reformulated more closely to a contrasted learning problem. And they've used this to train physical neural networks because once you have layer-wise cost function, you can imagine it's much more manageable to train physical system. And this is an example where practically they provide positive example of data, negative example of data, and they do this layer-wise training, right, as you can see there. And that blue box is the physical neural network. Then here they use different types of system, optic systems, and so on, to show that this will work. Okay. So one thing that I would like to say, though, is that this always surprises me. Now I'll get a little bit ahead of myself talking about. I hope I will. Yeah, I will start some discussion. But if we look every time at the optimization of the learning curves of backpropagation versus approximations of variance and so on, what we see is something like this. So this is even the simple MNIST data set, right? So it's really a toy problem. But still, what we see is that backpropagation, the black one, is much faster to train in comparison to direct alignments or other algorithms. And here, that bio-inspired algorithm is a mixture of different learning rules optimized to be fast as possible. And still, it cannot really reach the backpropagation speed of learning. And the thing that it's always surprising is that still backpropagation is not really fast. We know that. And so what is going on? Well, the only instance, I think, at least to my knowledge, where there is a bio-inspired algorithm that can surpass backpropagation is predictive coding energy-based network when the batch size is really low. So it has been shown that. But at the same time, you pay a big price in terms of when you have an energy-based network, you need to relax the network tune time in order to compute your weight update. And so if you are simulating that on a computer, you pay a big price. Of course, if you have a system that is not relaxing, that's a completely different story. But that's the only case that I know of where we have a biological inspired algorithm that is actually faster. So, I should have given a better title to this slide, but my idea of why this is happening is because we always neglect some form of structure when we train neural networks. Like every time we start from randomized connectivity, and probably, backpropagation is good in that term, in that sense, to start from randomized connectivity. But at the same time, if we want to have learning processes that learn from a few examples, that's not going to happen easily if we start from random connectivity, right? And indeed, we know that biological processes are not learned from a few examples. We do it all the time. First, our brain is much more sophisticated, but still. And this ability of learning from a few examples is typically faced in few-shot learning algorithms, right? Particularly, it has been the focus of meta learning, a topic that I'm quite excited about, even though it's not really new. And the idea is, rather than optimizing a network for inference, simply, you want to optimize the network such that it can adapt quickly to new tasks and new data, alert that will treat. And usually, this takes the form of a bi-level optimization process, where you have a family of tasks. So, for instance, this index I, right, are different tasks, and you define a cost function for each task. You have a global optimization process that is simply the sum of all those functions, okay? And you have task independent and dependent parameters. So you have some theta that are task independent, they're global, and then you have task dependent parameter theta I. And you practically want to perform this B-level optimization where you want to optimize theta such that the overall loss function is decreased, but at the same time, you condition the theta I for each task on some algorithm that starts from these global parameters and goes and find the minimum. So what this means in practice that if these are different tasks, what we're doing, and these are like weights in 2 dimensions, so these are 2 example of weights, what we're doing is that we're optimizing the initial condition, the initial starting point, so that we can get to the local minimum for each task as quickly as possible, okay? And so this, of course, means that we are treating the learning process as a dynamical process that needs to be optimized. And this is particularly interesting for me because if we could do this on neuromorphic computing systems, then, we will have systems that can adapt quickly to new tasks. Of course, this is challenging, but there has been some recent research showing that this is possible. We had some work on this, on some heterogeneous system to show simply that, for instance, heterogeneity can work for can help to achieve these few shot learning capabilities. Okay, so having said this, I almost finished with this introduction. So is backpropagation still relevant to train physical neural networks? And in my opinion, yes. There was this recent paper that I found really exciting, where practically what you do, you have a physical neural network, you don't know its transformation, you don't know anything about the function that the physical neural network is doing. And what you train a digital twin. So you train a model to behave like the physical network, to replicate its behavior. And then you can use that model to estimate gradients of your physical system. And in this case, they train it in that way. So here is where we came a little bit with this work. And because we wanted to face the most challenging case where your physical system has dynamical properties, is stochastic, and so it's really, really hard to train interconnected devices in that sense. So this is these are all the people involved for this work that is now under revision of Nature Communications. And the idea is, yes, we have different devices. We want to learn how to connect them. They have dynamical properties and they are stochastic. Not only that, but we have the problem is that we have no idea on what transformation they are doing. So we don't have any mathematical description that for how they behave. So an idea will be this is a simple video of one of the devices that we studied behave. And as you can see, it has these dynamical properties. This is stochastic. These are different realizations given the same input. And we don't know how it operates. We don't have any mathematical description. So the idea to do this was, okay, let's use an approach that is similar. Let's use digital twin. And let's use brute force, kind of brute force this, and use backpropagation through time on this type of system. So we got the data from the system, from the devices, the different devices, and we create a digital twin of this device. So we create a model that is able to replicate the device behavior. And then what we want to do is that in simulation, we optimize the connectivity, so how these devices are connected among each other. And then we transfer this optimized connectivity to the experiment. And we hope that the process works. And this has been really challenging because, of course, in any stage of this pipeline, some can get those wrong, not before. And so, of course, this is our idea of, how we represent that we do this simulated task optimization, and then we transfer the optimized plates for the task that we consider. In this case, we did it also for prosthetic control tasks that are relevant for real world. So how do we create the digital twin? That's the first thing. It's a dynamical system, and we don't have a mathematical description of what we do. This system is driven by an external signal S. We can measure some information of the device that here we say XI. And actually, what we need to do is that we need to go from this representation XIT to a new latent space, YIT, okay? This is the device I, such that we can describe the system as a differential equation. The idea is that if you remain in the space of XIT, it might not be true that your representation enables the system to be Markovian. You might not be able to predict the future, right? You might only observe a specific feature of your system, and the large majority of your system behaves remains uncharacterized. What we want to do is to consider history of XIT and go to a latent space where practically you can describe your system as stochastic differential equation. Also, now if you do that, then what we can do is that we can learn this f and g function. The f is the deterministic component, the g is the stochastic component, in a data-driven fashion. And so we can use neural networks to particularly learn this two function, such that our simulated behavior corresponds to the assessment. So how does this work? Well, I'm not going to talk about all the details on this part over here, but practically we got the data, on the system, we train on segments of trajectories, and we optimize this type of architecture that is composed by it's a neural network, of course. It has a deterministic block, a stochastic block. It's called a neural stochastic differential equation. And practically, we trained similar to generative adversarial neural networks, such that the behavior of the system reproduces, like the behavior of the model reproduces the behavior of the system. There's not only of the deterministic parts, or deterministic threat, but also it can reproduce its stochasticity. And we will see why I'm putting so much emphasis on the stochasticity, because otherwise you will see the training will fail. So after training, so these are like, I don't remember, but the red ones I think are the device, the yellow ones are the response of our system, even state input. And so we can reproduce the behavior, the distribution is given by the model, and so on. So practically, we can create digital twins. Of course, this required a lot of data. You need to get a lot of data from your device, but this is possible. And now what you need to do is that you need to, from here, you need to be able to estimate these terms, right? Because we need to do backpropagation now. And actually, we need to do backpropagation through time on these simulated devices. So we need to be able to estimate those terms, but without giving you too much mathematical details. This is simply, you can estimate it simply, and thanks to the fact that you have a mathematical description. And so if this is your neural SD model, practically you can compute the gradient with respect to your model to give you the estimate of the physical gradients, so of the dependencies of the system. Okay, so how does it work in practice? So if we try on analytical systems, so we first said, okay, let's try to see if this can work. So this is the fun oscillator. It's a simple dynamical system. And we want to study if we can approximate not the forward pass only, we can do that, but also the backward pass, so the dependencies. And so what we can see simply is that these are the two lines. The one is the model, the other one is the analytical system. And yeah, they overlap quite well. So after this, we were quite happy. We checked that this can be done in practice, and we did it also in different ways. So we tried to add stochasticity. We tried to check it practically in different ways that we can learn the backward pass of this physical system. In this case, it's a simple toy model. And this is another way to show this exact same thing, that we can learn the backward pass. Okay, so once we've done that, we had some system. In this case, they are nanorings or artificial spin vortex ices that we use for this demonstration. So we face two tasks. So the first one, of course, is the amplest. Why not? But here, at least, we made it more challenging because we wanted to make it temporally dependent. So we hide a high proportion of the image, and we present it in this way, as you can see, through time through the network. So the network needs to remember in order to perform that. We feed this into a network of rings. And of course, what we've done is simply we optimize the simulation and we transfer the connectivity to the experiment, and we hope that this works. We did it also for this prosthetic control task. So the first here, it's for the animase data set. This is for prosthetic control, where practically you want to control a prosthetic hand from SEMG signal gathered from the forearm of a subject. And yes, so these are the results. So practically, as you can see, we are using a neural ODE. So a neural ODE is a digital twin without understanding of the stochastic component. And you can see that practically, if we train on the neural ODE, what I want to show is that these, with the dots, will be the transfer to the physical experiment, right? And so, as you can see, simply, the neural ODE will always be optimistic. It will predict great performance in simulation, but then will fail in the experiment because it's not modeling the stochasticity of the system. While the neural SDE is quite accurate at predicting how the system will behave. And we, of course, did it for 1 layer, 2 layers, then we did it for 4 layers, but on another problem. But as you can see, this is always the situation. And that means that capturing the stochasticity, being able to model it actually is a key component to train this system. And At the same time, that baseline that you see over there is thanks to a reservoir computing framework. So if you try random connectivity or you try something else, well, how would the system behave? Those will be the performance. And this is the performance for the neuroprosthetic task that we face. And practically, we are always on par of, let's say, digital neural networks, given the same structure. But of course, here the task is temporally dependent. So it has some complexity in that sense that we're using the dynamics of the system as temporal memory. I should have said that, but yes. Another thing that we tried is that classification tasks are quite easier because you can be quite wrong in a classification task. The most important thing is that one device needs to have the right output node needs to have larger activity than the others. And indeed, loss functions as softmax cross entropy and so on are much more easier to handle than, for instance, mean-square error require precise activity from the node. So we try to face a regression problem, and the typical one is max-class prediction. So that's what we did, and we realized that nothing works because you accumulate easily error to your network structure, and even if you have a tiny error and you require precise activity, yes, the transfer will not work well. So what we try to do here is to use cascade learning. So rather than training everything together, you train one layer at a time. This is a well-known algorithm in deep learning. And the idea is that it's like training one hidden layer network at a time and going deeper and deeper. In this way, what you can do is that you can gather experimental data every time that you train a hidden layer to correct your system activities. And in this way, practically what we can show is that this results over here where we can get to arbitrarily different layers. Of course, here, these are for 3 layers, but we tried also for 5, 6, and so on. And you can see that if we don't use cascade learning, right, as we go from 2 layers to 3 layers, the performance gets worse because we're accumulating errors. While if we don't use, if we use cascade learning, the performance gets better and we get them to these nice regression results. So, yeah, so final thoughts that I wanted to say simply, this is kind of my opinion, but training of physical neural networks present new challenges. I think we need to kind of try to move away from backpropagation. But we'll see it's not incredibly easy. And at the same time, backpropagation can still provide a baseline in terms of trying to explore how the system will behave, trying to find a starting structure if you want to think about it in a meta-learning sense, and so on. Another thing is that we showed that digital twins can provide an effective way of how to train these physical neural networks. So with that, thank you for your attention. And do you have any questions?
So if you maybe probably tell us about what the missing reference.
Yes.
Then this data set 12 was.
Yeah, so on the task force, right?
Yeah. Was it physical?
So here what we're doing is that we have, I'll say it without, So we have this system of null rings. So they are dynamical physical devices. And the tasks that we're facing require some memory. So in order to...
What kind of devices?
Yeah, so in this case, they are nanorings or artificial support exercises. So what nanorings are magnetic system where practically you have magnetic rings with domain walls. You drive that text to a magnetic field. You will have domain walls that are moving and they are interacting among each other. And you measure that magnetization of the system. Practically what it does is that nearby rings will interact and you will get linear transformation out of them because of this. And they have memory because there is a relaxation time and so on in the system.
Like use them on the digits, so obviously.
Yes, exactly. So
and then this.
Yes, exactly. So practically what we do is that we take its systems. We don't know, like they were before modeled thanks to agent-based modeling approach. We did not know how to describe them mathematically. We train a digital twin to provide that approximation. And then we train the digital twin on any task, a network of digital twins on any task. And then we try to see if a network in the experiment of this system will work on the same task and reach the performance that we imagined. And yeah, and we show that it worked for benchmarks, of course, but it's still, I think it's still interesting that it could work without any mathematical prior or of the system in question. Yeah. I hope I replied. Yes.
Yeah, thanks for that. Really interesting thought. I was wondering, by training, presumably there's some analog behavior that you block, which is why you're using these systems for the bonus lakes. By training with a digital approximation, is there some risk that you almost overspend and you're analyzing the system starts approximating a digital QoS?
Yeah. So like, so I think you, like, in terms of risk, we're using models that are good for continuous type of system. Of course, yeah, there is this convergence, that's true. But it still can all, of course, like what I have to say is that we laugh about this because it's somehow we are moving from energetically kind of inefficient system to also energetically inefficient training algorithms in some ways, where you create a digital twin and then you train this. But at the same time, I think this is really good to explore in the sense that how would you be able to train complex dynamical systems that are interacting? And that's a challenging question. And so we wanted to provide a solution to that in any way possible. And that's true that there are practical, limitations. But yes, and yeah, I know what it is.
But there was scripts. Be the maybe is like you assume that you expose what possible odds.
Yeah. So that's a good question. So you wanted to gather enough data so that your system is characterized. Now this is tricky. Higher the dimensionality of the system, more it becomes challenging. What we did is that we gather it in a regime. I didn't explain all the detail, but we gather it in a specific regime, and then we constrain the training of the network such that the input to the device is the same regime. That was a big trick not to get lost into the space. Yeah, so we knew there were some regimes with no linearity, so we get our data there, we characterize there, and then we constrain the network to input to each device. Otherwise, that would be a time. Okay, thank you. Thank you.